Deflection of a beam. Consider a beam of the length L, which is homogeneous in material and has uniform cross sections along its length. And there is the axis of symmetry, which is a straight line joining the centroid of all its cross sections. This beam is supported on the left end and the right end. The weight of the beam distorts the axis of symmetry into the curve as the second figure here. And this curve is called deflection curve or the shape of the beam. And we are going to investigate the function that representing the deflection curve. In this case, we use the notation y as a function of the x. Suppose x-axis coincide with the axis of symmetry, so deflection as a y as a function the x measure from this axis and is positive if it's downward. The bending moment m at the point x along the beam is related to the load per unit length, which is the w of the x. As the equation, the second derivative of the moment equals the weight function. The bending moment m is proportional to the curvature k, as m equals the ei times k, and E is the Young modulus of elasticity of the material of the beam. I is the moment of inertia of the cross section of the beam about the axis known as the natural axis. The curvature as the form of y double prime divided by 1 plus y prime squared, the quantity raised to the power 3 halves, where y is the deflection. As a sequence of the theory of elasticity, when y is small or the deflection is very small, comparing with the unity 1, so the y prime approaches 0, or we assume y prime is 0, so the y prime is gone. The curvature k is approximately equal to y double prime. And the m is ei times y double prime. As the second derivative of the m with respect to x is w, so we find the second derivative of the m as ei times y double prime to get the fourth order differential equation representing the deflection of the beam as the ei times the fourth derivative of the y equals the wx as a weight function. The boundary conditions for the beam problem. If one end or the end is embedded, the boundary conditions at that end is y equals 0, y prime is 0, or no deflection, and the slope is 0. If the end is free, the conditions will be y double prime equals 0 and y triple prime equals 0, as the bending moment is 0 and the shear force is 0. If the end is simply supported or hinged, then the boundary conditions at that end will be y equals 0 and y double prime equals 0. Or we can say it's no deflection and the bending motion is 0. Examples: the beam is embedded at its left and free at its right end, and the W equals 24 times EI. The length L equals 1. We are going to solve the deflection equation as EI times the fourth derivative of the Y equals the W, and we're going to find the maximum deflection of the beam after that. With the boundary condition at the left end, which is at x equals 0, is embedded on the left. So then the condition will be y at that end equals 0 and y prime at that end equals 0. On the right end, which is x equals 1, as the length equals 1. So x equals 1 is free. So the condition for that end will be y double prime at 1 equals 0 and y triple prime at 1 equals 0. Then from the equation, we just rewrite it as ei times the fourth derivative of the y equals to w. This case, w is 24 times ei. So ei and ei cancel, becomes y to the fourth order, or the fourth derivative of the y equals 24 with the four conditions. And then we are going to find the antiderivative to get the deflection y 4 times. So for the third derivative, we get 24 times x plus c1. And with the condition y triple prime at 1 equals 0, so 0 equals 24 times 1 plus c1. Therefore, c1 equals negative 24. Now we have y triple prime as 24 minus 24x minus 24. And next, find the second derivative by doing the antiderivative of 24x minus 24 to get 12x to the second minus 24 times x plus c2. And from the initial condition, from the boundary condition y double prime at 1 equals 0, we get 0 on the left as a y double prime value equals 12 times 1 minus 12 times 1 plus c2. This is 24, sorry. So then the c2 is positive 12. And now we get y double prime as 12x squared minus 24x plus 12. And next, we find another antiderivative to get y prime, which is 12 divided by 3 or 4x to the third minus 24 divided by 2 or 12 times x squared plus 12 times x plus c3. So y prime at 0 equals 0. That 0 equals c3. That's simplify y prime to be 4x to the third minus 12x squared plus 12x, and do one more antiderivative to get the y or the deflection function. Y equals x to the fourth minus 4x to the third plus 6x to the second plus c4. So with this, we have one more condition to use, which is y at 0 equals 0. So y at 0 equals 0, and 0 equals 0, 0, 0, c4, or c4 equals 0. Then the deflection function as y in the function of the x equals x to the fourth minus 4x to the third plus 6x to the second. Which is the deflection equation. And then part B. Part B, we are going to find the maximum deflection of the beam. Or deflection Y. It occurs when y prime equals 0. And from y prime that we obtain during the process, y prime is 4x to the third minus 12x to the second plus 12x, and then let it be 0 to solve for x or the position that give the maximum deflection. Then solve for x factor 4x to get 4x multiplied by x squared minus 3 times x plus 3 equals 0. We get x equals 0 and solve this quadratic equation to have x equals negative b plus minus square root of b squared minus 4 times a times c. 4 times 3, that's 12, divided by 2 times a. And the discriminant is less than 0, so then there's no real solution for the second factor. Therefore, the deflection occurs at x equals 0 or on the left end. That means the maximum y equals, replace x with the 0, so y at 0, which is 0.